Okay, so welcome back. In this second unit of this introductory module, I've called it Why Portland Cement. And what we're going to look at in this module is why the composition of cement is as it is. Why Portland Cement? 99.99% of cement made today is based on what we call Portland cement, or more precisely, Portland cement clinker. So clinker is these nodules you see in the picture here. And that's the material that comes out of the cement kiln. And the name Portland, this is purely a marketing name. This was chosen by Joseph Aspdin, who was the person who patented the term Portland cement in 1824. And what he wanted to do, he wanted to highlight the appearance of his new material to Portland stone, which was then regarded as the best building material in England. So don't worry about this word Portland, it's purely a marketing term. So the dominance of this type of cement is really not by chance. It's a direct consequence of the raw materials which we have available on Earth. So here on the left, we see the composition of the Earth's crust. And it's really remarkable to see that we have just 8 elements, that's to say oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. These together make up more than 98% of the Earth's crust. This is quite remarkable, but those of you who may have done some astronomy will realize that it's a direct consequence of the formation of elements in stars. And it also means that this is not just the composition of the Earth, but will be the similar composition for all the rocky planets we can imagine in the universe. What this means is that even elements we regard as quite common, like for example copper, are very, very much less abundant than these 8 rock-forming elements, like for example silicon. And this relative abundance of 1 to 1,000 will translate in terms of the availability and the cost of these materials. So having seen in the last module how the very large amount of the cement that's produced, clearly we can't think about making cement out of all the other elements that's in that remaining 2%. So now we can understand that it's the composition of the Earth which limits the practical chemistries we can have for cementitious materials. But looking on the bright side, it also means that we can explore all possible options. It means that there's no kind of breakthrough out there that we haven't discovered yet. And what we need to really know in a bit more detail is how cement works to understand how these different elements can be used. So this is what I've illustrated in the next few slides. So this schematic here really tries to explain this. When you mix grey cement powder with water, what you have is grains just floating about, and that is very convenient because it means you have a flowable material you can cast into molds, you can make into different shapes. And then we have a chemical process whereby these grey cement grains are dissolving, and then the ions are reacting with the water to give us this new solid, which are called the hydrates. So in this image here, the red areas are the cement hydrates. And these have a higher volume of solid, and therefore it holds the cement grains together, creating a rigid solid. So let's go back and look at this composition of the Earth. Most of those elements are associated with oxygen as oxides, and look at whether these different oxides can react to give us the cementitious material. Now, if we take the 2 alkali oxides, sodium and potassium, the problem here is these produce very, very soluble salts. So maybe in your chemistry lessons, you've used sodium hydroxide, and you'll know that you can have very strong sodium hydroxide because a very high amount can go into solution without precipitating. So clearly this is no good for producing solid hydrates which hold the structure together. On the other hand, if we look at iron oxide and magnesium oxide, the problem here is that these oxides have fairly low mobility in alkaline solutions, which is the solutions we have in cementitious materials. So what we can see in this image here, this is just a piece of concrete taken from a normal concrete wall. And in this image, we have some very bright areas. And these very bright areas are where all the iron oxide is located. And in fact, those bright areas are exactly the same as in the original cement grains. During that whole 30 years, that iron in the cement grains has just stayed in the same place. So it's not doing any harm, but basically it means it's not going out into solution, it's not precipitating new solids, and therefore making very little contribution to the bonding and the development of strength. It's a similar story for magnesium. Here in this picture now, we see a blended cement. We're going to talk about that in a few modules' time. And in this blended cement, the darker grains, such as in the center of the picture here, you see are now surrounded by a region of dark products. And these darker products are because all the magnesium that was in that slag grain is concentrated in that area. And same situation, this magnesium has not moved into the space between the grains. It's not really contributed to bridging the space between them. So this means we end up with just 3 oxides, which are really the most useful, and are the essential component for the Portland cement we have today. So this is really in no way a coincidence that we've ended up with this composition. Because if we now look at that ternary system between calcium oxide, silicon dioxide, and alumina, we see the composition of Portland cement. And in fact, Portland cement, as we see it here, this is composed of calcium silicates. There's really only one other region in this diagram where we have minerals that will react with water in the way we previously saw and give us cementitious materials. And that's this region here, which is the region where we find calcium aluminate cements and calcium sulfur aluminate cements. Small amounts of sulfur is the sort of extra dimension which is not shown in this diagram here. So these other compositions, calcium aluminate, calcium sulfur aluminate, have a lot of advantage because they have less calcium in. You see, they're further away from that calcium oxide corner, means they have less calcium oxide, and therefore there's less CO2 produced chemically during the production of these phases. So that sounds very good, but the problem is that it's not so easy to make these because the raw materials we need are not so widely available. And we have to ask the question, what sources of minerals are there which contain much higher amounts of aluminium to silicon? Most minerals have about the same ratio of silicon to aluminium as in Portland cement, about 2:1. To get a composition down here in this alumina-rich part of the diagram, we have to go to materials like bauxite. Now, bauxite is much more localized than the materials used for making Portland cement. It's estimated that only 10 countries contain about 90% of the reserves of bauxite. And of course, bauxite is the first raw material for aluminium production. So the consequence of all this means that it's rather expensive. And it means that you cannot produce calcium aluminate cements or calcium sulfur aluminate cements for the same cost as producing Portland cement. We can look at this effect of chemical CO2 and how it's related to composition in more detail on this slide here. So at the top, we see the 2 calcium silicates which are present in Portland cement. These are known as tricalcium silicate or C3S, dicalcium silicate or C2S. And many people have proposed that what we should be doing is making Portland cement with more C2S as opposed to C3S. But the problem here is that the reduction in chemical CO2 is really very marginal. It's only around 10%. And that's more than offset by the much slower kinetics of C2S. So the strength development is much slower, and because the strength development is much slower, this would mean that in practical situations where people need a given strength at a given time, then they will use more cement. And that use of more cement will completely cancel out this 10% saving. So B-light-rich clinkers really don't contribute at all to lowering CO2 emissions. Down here, we can see the figures for yellowmite. That's this complex phase called C4A3S bar. And as I said on the previous slide, this has a good reduction potential in terms of lower chemical CO2. But we have the problem of the cost of the raw materials. And finally, on this slide, I want to point out this line here, because many people nowadays are proposing that we should use magnesium-based cements. There can be context in which this might be possible, not now, but if somebody can invent a way of producing magnesium-based cements from magnesium silicate rocks, it might be interesting. But what's happening at the minute, most people are using magnesium carbonate, and what you can see here very clearly is that the chemical CO2 emissions from breakdown of magnesium carbonate are way higher than they are from the calcium silicate phases we have in Portland cement. So here we come back to that composition of the earth we've discussed in detail, and we compare it with the composition of a typical Portland cement. And you can see the elements present are similar. The big difference between the Portland cement and the composition of the earth is the dominance of this sector for calcium. And this is, as we explained in the last lecture, where the chemical CO2 is coming from. But from a practical point of view, it's very easy to make things with this composition because limestone, which is usually very pure calcium carbonate, is very widely distributed across the globe. And it means that you can make these Portland cements out of limestone. The other elements are generally coming from something like clay, but you can make this almost everywhere in the world, and therefore transportation of the final product is minimized. So the other important aspect is the pattern of reaction of the Portland cement. And this is shown in this diagram here, which plots the heat evolution, which is a signature of the rate of reaction. And what we can see is at the beginning of the reaction, we have a burst of reaction, and then we have this period here where the reaction remains slow for several hours. From a practical point of view, this is extremely important as it gives us time to mix the cement and transport it to the building site. And then after about 3 hours, the reaction takes off again. Now, this pattern of reaction means that really it's very, very simple to use cementitious materials. Here we see a picture from India where people are making concrete under really quite rustic conditions. But nevertheless, because it's such a robust chemical reaction, it still works. It still gives very good quality building materials. Really, what we're going to see that for these reasons I've explained to you here, cements based on Portland clinker will be the most important materials for the foreseeable future. They can be made from widely available raw materials. There's an incredible economy of scale, leading to very low cost, and they're very easy to use even by unskilled workers. Given the composition of the earth, this composition Portland cement clinker really is the best option. But in the next lecture, what we're going to see how by replacing part of this Portland cement, we can lower environmental impact. So thank you very much.